Two planets that orbit each other form a so-called double planet system. Consider a double planet system of two spherical planets, one of radius p, the other of radius q, with p less than q, and whose centres are separated by a distance L. An observation satellite is to be placed on the line joining the centres of the two planets. Part A. Find the position of the satellite that maximizes the surface area of the planets that is visible to the sensors on the satellite. So first we draw a diagram. Here are the two planets with radius p and radius q separated by a distance L. We call the smaller planet on the left S and the bigger planet on the right B. The satellite lies on the line joining the centres of the planets. We have to find the position of the satellite, so we set up a coordinate system and we say that the satellite is a displacement x from the centre of S. We are interested in the surface area of the planets that is visible to the sensors on the satellite, and we see that the area visible on planet S is contained in this cone, and the area visible on planet B is contained in this cone, and we call the two areas AS and AB respectively. Now we have to maximize A, which equals AS plus AB, and if we can find an expression for A in terms of x, we can differentiate it and thus find a maximum. First though, we need to find expressions for AS and AB, but there is a hint in the question that we can use to do so. And the hint is this: the curved surface area of a spherical cap subtending 2 theta radians at the centre of a circle is given by the formula A cap equals 2 pi r squared into 1 minus cos theta. And a spherical cap is a part of a sphere generated by the intersection of a plane and a sphere. So a spherical cap looks like this, and if it subtends 2 theta radians at the centre and the circle has radius r, then the area is given by the stated formula. So we can see from the diagram earlier that both AS and AB are the areas of spherical caps. But we want to express these areas in terms of a displacement x rather than an angle theta. So here we have the planet and the satellite at a displacement x, and the tangent line makes a right angle to the radius by circle geometry. And since this is the angle theta, then we have the cos theta equals r over x, so that the formula for the area of the cap becomes 2 pi r squared into 1 minus r over x. Now we can note two things using this formula. First, as x tends to r over x tends to 1, so that A cap tends to 0. And this says that when the satellite is very close to the surface of the planet, it sees almost none of its area. Second, as x tends to infinity, r over x tends to 0, so that A cap tends to 2 pi r squared. And this says that when the satellite is very far from the planet, it sees roughly one whole side of the planet's surface. And both of those results agree with our experience. From the Earth, we can see one side of the moon, more or less, but when astronauts landed on the moon, they could only see that part of the moon that was in their local vicinity. So here are planets S and B, with the satellite x displacement from the centre of S. From the diagram, we can see that the satellite is L minus x from the centre of B, and that x must lie between P and L minus Q inclusive. And so using the formula for the area of a spherical cap, we have that AS is this quantity, and that AB is this quantity. So that A, which is AS plus AB, becomes 2 pi p squared plus 2 pi q squared plus 2 pi into q cubed over x minus L minus p cubed over x. Now to find the value of x that maximizes a, we differentiate the expression above and set it equal to 0 as follows. And on solving the resulting equation, we obtain the following quadratic equation: q cubed minus p cubed times x squared plus 2p cubed lx minus p cubed l squared equals 0. And we solve this quadratic equation in the usual way via the quadratic formula. To find that x equals minus p cubed plus or minus the square root of q cubed p cubed over q cubed minus p cubed times L. So now the question is, should we take the positive or negative square root? Well, first we can see that q is greater than p, so that q cubed is greater than p cubed, so that q cubed minus p cubed is greater than 0. And so this denominator is positive. And now we note that since the satellite has to lie between the planets, then we need x to be greater than or equal to p, which is greater than 0. And so we certainly need x greater than 0, and if we were to take the negative root, then x would be negative, because the numerator would be negative, and so we must take the positive root. And so we have that x equals the square root of q cubed p cubed minus p cubed all over q cubed minus p cubed times L. And now we need to check that this does indeed maximize the area A. And to do so, we will use the second derivative test. Now since a prime equals 2 pi into p cubed over x squared minus q cubed over x minus L squared, then a prime prime, the second derivative, equals 4 pi into q cubed over x minus L cubed minus p cubed over x cubed. Now for a maximum, we require a prime prime be negative when x takes the value as shown. And if we can show that both terms in the formula for the second derivative are negative, then we are done, and we will proceed to do so. First, we show that x is indeed greater than 0. So first we note that q cubed is greater than p cubed, which is greater than 0, so that q cubed p cubed is greater than p to the 6 on multiplying both sides by the positive quantity p cubed. And we take the positive square root to show that the square root of q cubed p cubed is greater than p cubed, so that the square root of q cubed p cubed minus p cubed is greater than 0. In addition, we have that q cubed minus p cubed is greater than 0, and so with this quantity and this quantity being positive, then we have that x is also positive. But since x is greater than 0, then minus p cubed over x cubed is less than 0, and so this term is negative. And now we consider the sign of x minus L. We know that p cubed is less than q cubed, so that q cubed p cubed is less than q to the 6, so that the square root of q cubed p cubed is less than q cubed, and on subtracting p cubed from both sides, we have that the square root of q cubed p cubed minus p cubed is less than q cubed minus p cubed, so that the square root of q cubed p cubed minus p cubed all over q cubed minus p cubed is less than 1. And on multiplying both sides of that inequality by L, we find that x is less than L, so that x minus L is negative. And from that it follows that q cubed over x minus L cubed is also negative. And hence the other term in the expression for the second derivative is also negative. And so with the given value of x, we have that the second derivative is negative, and so this value of x maximizes the visible area A. Part B. By use of a suitable substitution, evaluate the limit as x tends to 0 of the cube root of a cubed plus x minus a all over x, where a is a real number. Now, if a function is continuous, which means its graph when drawn has no breaks, then there is a very simple result, and that is that the limit as x tends to a of f of x equals f of a. So for example, given f of x equals x squared plus 2x plus 3, which is continuous, then the limit as x goes to 1 of f of x equals f of 1, which equals 6. And so if we ignore the suggestion that we use a suitable substitution, we may ask, can we just do the same thing here? Can we plug in the value 0 to the formula whose limit we need to evaluate? Well, if we do so, we very quickly see that we end up with the form 0 over 0, which is undefined. So the answer to that question is no, we can't. We'd better look at solving the problem by using the suitable substitution. Now, we have this expression, and the most complicated part of it is this, the bit under the cube root sign. And so we naturally wonder, can we make this look nicer with a substitution? And our first try might be to set a cubed plus x equal to u, in which case we find that the whole expression turns into the cube root of u minus a all over u minus a cubed. And that clearly looks worse. And what we really want to do is to eliminate the cube root completely. I.e., what we want is the single variable u being equal to the unpleasant expression, the cube root of a cubed plus x, from which we find that u cubed equals a cubed plus x, so that x equals u cubed minus a cubed. And then the expression in question turns into u minus a all over u cubed minus a cubed. And this clearly looks a lot nicer, and it looks nicer because it only involves polynomial terms. So we will try to continue the problem with this form of the expression. Now we have that u equals the cube root of a cubed plus x, and so as x tends to 0, then u tends to the cube root of a cubed, which equals a. And so the limit as x tends to 0 of the original expression becomes the limit as u tends to a of u minus a all over u cubed minus a cubed. And now we can note that we can factorize this expression, u cubed minus a cubed. And in fact, we have u cubed minus a cubed equals u minus a times u squared plus au plus a squared. And so our limit turns into this expression, where we note that we have a u minus a on the top and on the bottom of the fraction. And in fact, we can divide away this u minus a as long as u is not equal to a, but that is always the case when we are taking the limit. And so we end up with the expression, the limit as u tends to a of 1 over u squared plus au plus a squared. And now we turn the limit of a quotient into the quotient of limits, and from that we find that the limit is equal to 1 over 3a squared, where we have evaluated this limit by noting that u squared plus au plus a squared is a continuous function, so we can use the fact that the limit as u tends to a of f of u equals f of a. Evaluating limits can be pretty tricky, and it would be nice if we had some other way to evaluate this limit so we could check our result. And in fact we can do so. We can evaluate this limit in a fairly quick and dirty way by using a binomial series expansion. So we can rewrite the cube root of a cubed plus x as a into 1 plus x over a cubed to the power 1/3. And using a binomial series expansion for that expression, we have that it is approximately equal to a plus x over 3a squared when x is close to 0. And when we evaluate a limit as x tends to 0, we are interested in the values that an expression takes on when x is close to 0. So this is precisely what we want. And so using that expression for the value of the cube root of a cubed plus x when x is close to 0, we quickly see that the cube root of a cubed plus x minus a all over x is indeed close to 1 over 3a squared when x is equal to 0. And that confirms the result for the limit that we found earlier. Showed that when the planets are of equal radius, the satellite should be placed midway between them to maximize the visible surface area. So we know that we maximize the visible surface area when x is given by the formula shown here. Also, when the planets are of equal radius, p equals q. And we can think of x as a function of p, x of p, and we need to show that x of q equals L over 2. So it seems that we merely need to substitute q into the formula for x of p. But if we do so, we immediately see that we get an undefined result, 0 over 0 times L. So that doesn't work. So x of p is not defined when p equals q. It is defined, however, when p is less than q and p is greater than q, because in those cases the denominator is never 0. So we can't find x of q by direct substitution. On the other hand, if p was very close to q, then we may hope that x of p would be close to L over 2. But of course that's exactly what a limit tells you. The value that a function approaches as its argument approaches some value. And so we can investigate the question, can we find the limit as p tends to q of x of p? And now we might wonder if the first part of this question, where we had to evaluate a limit, was in fact a hint. So we have the function x of p, and we have to find the limit as p tends to q of x of p. And earlier we found this limit. And we can note the similarity between the numerators of these expressions. So given the similarities, can we use a similar substitution trick for the limit on the left as on the right? If so, it's clear that we want to replace the square root of q cubed p cubed with a single variable, i.e. we want u equals the square root of q cubed p cubed, from which it follows that p cubed equals u squared over q cubed. Also, as p tends to q, u tends to q cubed, and so the limit that we want to find becomes L times the limit as u tends to q cubed of u minus u squared over q cubed, all over q cubed minus u squared over q cubed. And we can evaluate this limit similarly to what we did with the limit involving x earlier. So we have that x of p is given by the formula shown for p less than q and p greater than q, and that the limit as p tends to q of x of p equals L over 2. And this means that we can define x of q equal to L over 2. So recalling that x of p is undefined at q, by setting L over 2 equal to x over q, then we essentially fill the gap. We remove the point at which the function is undefined. And in doing so, we make x of p into a continuous function without any breaks in its graph. And so when p equals q, x of p equals L over 2, and this maximizes the visible area when the planets have the same radius. Now that was all fairly complicated stuff, but there's a simpler approach, and that is to reanalyze the whole problem with the condition that p equals q. Earlier, we derived the following equation for the maximum visible area A. And so we can set p equals q in this equation and then find the maximum for this case. And when we set p equal to q, we find that A equals 4 pi q squared plus 2 pi q cubed into 1 over x minus L minus 1 over x. And now we find the derivative of A, set it equal to 0, solve the resulting equation to find that x equals L over 2, as we expected.